Geothermal energy has historically been produced by driving turbines with steam, or with more modern technologies like organic Rankine cycle systems. But new geothermal concepts like closed loop, EGS, and closed loop hybrids may usher in a paradigm shift in how electrons are produced from geothermal resources. Advanced turbines designed to operate with supercritical CO2 and thermoelectric generation, which would allow for downhole energy production, are on the horizon as potentially disruptive redesigns of topside geothermal operations. What stage are these technologies in development, and how far are they from commercial reality? What are the benefits and challenges associated with these new technologies? What entities are trying these techniques in the field? Let's explore.
Hello, everybody. Welcome and thanks for joining. My name is Michael Campos. I'm with Prime Impact Fund, a seed stage venture firm investing in breakthrough climate technology companies. First, a big thanks to the Pivot organizers and production crew for putting on a top-notch event. Please help me show them some love with the reactions button at the bottom right of your screen. And please don't be shy about hitting that reactions button throughout the panel. So at Prime, earlier this year, we made our first geothermal investment in a company called Zanskar, which does predictive exploration. The CEO actually presented at Pivot earlier this week. And as a quick plug, if you're interested in how venture capital and geothermal intersect more generally, my teammate Johanna Wolfson will be speaking on a panel all about venture capital tomorrow at 5:30 Eastern. So my personal history in geothermal goes back a couple more years, back when I was at the US Department of Energy's Advanced Research Projects Agency, or ARPA-E, and I get to help fund a variety of high-risk, high-reward geothermal R&D projects. This panel today will be a blue sky exploration in that vein, of two technologies that, if successful, could really revolutionize how geothermal energy is converted into electricity. The first is using CO2 as a working fluid instead of water. And the second is using solid state thermoelectric power generation to replace turbines. Why bother with any of this? Well, topside power conversion isn't all that efficient. One study found that the average geothermal plant is something like 12% efficient, with some breaking 20% by exception. And for reference, if you have a 200 degrees Celsius resource, the thermodynamic limit is somewhere around 35 or 36% efficiency. So my point is there's quite a bit of headroom. Today, I'm coming to you live from Boston, but we're lucky to be bringing you panelists from a couple of different continents. I know there's this audience is very, very lively and asks a lot of questions. So trust that we will leave plenty of time for questions toward the end of the panel. But for now, I'll hand it off to our panelists for a 1-minute overview from each. If you could each say your name, your organization, where you're calling in from, what technology are you excited about, and what's the bull case for it? Why don't we start with Brian, and then Jordan, and then Martin, and then Neil. Over to you, Brian.
All right, thank you very much. It's a pleasure to be here. My name is Brian Higgins, and I'm the CTO for Greenfire Energy. We are a closed loop geothermal startup, and our focus is on doing retrofit projects and then purpose-drilled well projects where we can circulate a number of different fluids, but supercritical CO2 has been one of our primary focuses, and we've demonstrated this recently. You can find a lot of details on our website as well. Thank you.
Hi, my name is Jordan Nilsson. I'm a senior research engineer at Southwest Research Institute. We are a private, not-for-profit research and development firm in San Antonio, Texas. And I specifically work in our machinery group, and we are focused on all things machines and turbo machines, and have done a lot of research at higher temperatures for power generation using supercritical CO2, and that kind of led us naturally into the geothermal realm as well.
Yeah, hello. I'm Martin Saar. I'm a professor for geothermal energy and geofluids at ETH Zurich in Zurich, Switzerland. We, in my research group, we do research on fluid and energy transfer in the subsurface. And I'm here today to speak specifically about combining CO2 capture and storage with geothermal energy extraction. So it's all about the CO2 transfer in the subsurface and how that affects the efficiency of electricity generation.
Neil, over to you.
Hi, good. Yeah, Michael, thank you very much. Hello, everybody. My name is Neil Kavanagh. I'm the Chief Scientist at Woodside Energy, Australia's leading natural gas company, and I'm speaking to you today from Western Australia. I'm an engineer. I'm also a director of the Society of Petroleum Engineers, and I've got a background in well engineering, actually. But in recent years, I've been in the innovation field, and I'm the Chief Scientist at Woodside Energy. And what's got me interested in geothermal, and in particular the simplification of geothermal wells and using solid state devices to make electricity, is that Australia exports a lot of LNG, liquefied natural gas, about 80 million tons per annum. It uses a lot of energy to liquefy that gas. We do have abundant renewables available, but it's intermittent. What we need is a mixture of baseload renewables as well as intermittent, and geothermal seems to be perfect, but it needs to be simplified and it needs to be cheaper. And I think that solid state could be the way to go.
Wonderful. Appreciate the overviews from everybody. Why don't we start with Neil? What's so hard about doing solid state thermoelectric conversion? Is this a fundamental materials problem, a geothermal specific application challenge, or sort of both?
Yeah, well, that's a good question. And there are a lot of problems to making it work. But first of all, I should say that thermoelectric devices definitely do work. And they're quite commonly used in spacecraft because they're so simple and reliable. And what you're talking about is two semiconductor strands that form a junction at the hot end and open circuit at the cold end. And on one side, you've got the N-type semiconductor with a surplus of electrons, and on the other strand, the P-type. And if you put the one junction in the hot, electrons will flow. That's a fact. But the reason why it's problematic is twofold. First of all, it creates quite a weak electric flow. And secondly, the geometry of the devices that are in common use are quite compact. The geometry is quite compact, and the distance between the hot and the cold side isn't very far. Whereas in a geothermal well, the distance between the cold at the top and the hot at the bottom would be in the order of 3 kilometers. So to make it work, a thermoelectric device in a realistic geothermal well would have to have wonderful conductivity, a very high Seebeck coefficient, and very, very low thermal conductivity. And it's a material science problem to find the right kind of materials that could really come up with something that worked very well.
Got it. So I think that's a great and very helpful overview to start with. Let's kick it over to the CO2 side of things. And maybe let's start with Jordan and then expand to our other panelists. So supercritical CO2 cycles were developed for other generally higher temperature forms of power generation. Are we using them elsewhere today? And what's hard about adapting them to geothermal?
Great questions. So we have done quite a bit of technical development for different types of turbomachinery and turbines for higher temperature. And the problem with those are generally materials related. For power generation, we're looking at a little above 700 degrees Celsius and not a lot of metals like that temperature. And even the ones that do have quite a reduced strength. And so CO2 is a great working fluid in that it provides benefits efficiency-wise. And so that's kind of one thing we've been researching. Moving that over to geothermal, the temperatures are a lot lower, so it's not so much a materials problem. It becomes a little bit more of the uncertainty of the CO2 flowing through the well. There's still not a lot that is known, and that's not even a lot of what Southwest Research Institute's expertise is doing things downhole. But I think there's still a lot of uncertainty of what's going to come out of the hole. And so designing a turbine for that application becomes making it modular and being able to run efficiently for a wide range of temperatures.
Got it. And Martin, maybe you'd be the next person to chime in on this as the subsurface reservoir scientist. Could you walk us through how CO2 behaves differently in the subsurface and overall in a power system, and what some of the relevant trade-offs to consider might be?
Sure, yeah, I'm happy to. So, so the idea of at least this version of using CO2 to extract geothermal energy is to combine it with CO2 sequestration. So you do general standard CCS. You inject the CO2 in a deep reservoir, so maybe 2.5, 3 kilometers deep, so a bit deeper than standard CCS depths. And then the CO2 gets geothermally heated in the reservoir. And then you produce from this big CO2 plume that establishes itself there, you produce from that CO2, and also water comes up there. At first, quite a bit of water, almost only water, and then it will mostly be CO2 after a few weeks, according to our simulations. And then you essentially have there's also water exsolving from the CO2 on the way up, which is nice because it produces additional energy because it's exothermic reaction. And then, but also it can cause liquid loading. So you have to be careful there in that stage, in the first stage when you turn it on. But then you bring it up to the surface, and ideally you run it directly through a CO2 turbine. So there, if you have water in there, maybe you want to take it out beforehand, but it's not as critical as with a steam turbine, where you really don't want to have liquid water droplets hitting the blade. Because the density difference between supercritical CO2 and liquid water is a factor of 2 approximately at those temperatures. And so the turbine blades can usually handle at least like 10, 15, 20%, we think, of water there. And then you still have that mass flow rate of the water adding to the CO2 mass flow rate. And then the mass flow rate times the enthalpy drop gives you the power output. Of course, there's some inefficiencies of the turbine itself. You cool it, you remove for sure any water before re-injecting the CO2, and you re-inject the CO2 together with the CO2 stream from the CO2 capture facility, so that all the CO2 is still 100% permanently geologically sequestered and no CO2 is released. So you basically have full CO2 sequestration, but you're borrowing the CO2 out of the reservoir to generate the power. And maybe one last comment, at least for now, on this is the important part that I want to emphasize here is that you roughly double the electricity generation rate compared to using groundwater or brine in the reservoir, and it has nothing to do with the turbine, but rather with the mobility of supercritical CO2 being roughly 4 times larger, 4 times that of brine under typical reservoir conditions. So all else being equal, compared to brine, you get 4 times the mass flow rate through your reservoir. And since the mass flow rate times enthalpy drop in the turbine is your power output, you would get 4 times the power, but since specific enthalpy of supercritical CO2 is 1/2 that of water under typical reservoir conditions that we envision, you get a power doubling of the electricity generation. And so any kind of what Jordan is looking at, the turbines themselves, the CO2 turbines, and any improvements in power output, that is not considered in this calculation. So we have here basically a doubling of the electricity output simply due to the improved mass flow rate through the reservoir itself.
I really appreciate how you've stated the trade-offs here in terms of, you get 4x the mass flow rate, but you have only half the heat capacity. So on balance, you're about, bringing twice as much power to the surface. So I want to move it over to Brian. So as a geothermal startup operator, how are you all at Greenfire thinking about using CO2? And in addition to the upside that Martin just stated, are there other upsides that you see in terms of surface footprint, ease of operation, or anything like that?
Sure, sure. So first, as by way of segue from open loop to closed loop, Greenfire actually started with this idea that Martin has proposed, where you would use CO2 injection, sequestration, and then pull off some power from it. And I think that's great. It's a big problem to solve with the geology, and so closed loop simplifies this by separating the working fluid from the heat, right? And and pumping that heat to the surface. So we analyze a number of different fluids. CO2 has some advantages and disadvantages, and one of the chief advantages is that you create, in a closed loop environment, and probably open as well, you create a thermosiphon effect. And this is kind of a neat idea. And basically, around the critical point, CO2 is very dense, approaching that of water. And so that's how we inject the CO2 into the well. We go down the inside of a tube-in-tube heat exchanger. That's it's a vacuum insulated tube, so it's heat insulated from the counterflow. And this, because it's so dense, creates a very large pressure at the bottom of the well. Then the CO2 turns the corner and it comes back, getting heat from the rock, and it changes the density quite a bit. And so it preserves that pressure to the top. And so it's the enthalpy that you produce is temperature and pressure. And so the turbines that you're considering are really optimized for a very large pressure drop to create the power. And that's really the advantage. It's quite efficient. And I probably lost all your questions we can get to later. But one thing I'd like to point out is the way we do our analysis of an installation, a reservoir, is to monetize all the components, predict the power that we can produce, and then optimize on the LCOE. We really think that's where it wins, to look at the cost of power.
Got it. Wonderful. So this is really fascinating stuff. And one thing that in my now couple of years of paying attention to geothermal that I've noticed is you can rarely turn one knob and expect to change just one thing. So I'd start with Jordan on this question. What are some system-wide effects that you might expect to change as a result of switching to CO2 as a working fluid? Well, let's start with Jordan, and if anybody else has other comments, we would welcome that.
So I'll kind of start where Brian left off. We've looked a lot into the thermosiphon of CO2, and actually built a small flow loop to kind of test that thermosiphon and set aside our model. But it becomes an interesting optimization problem in that you can restrict your flow and get a little bit more pressure and a little bit more temperature, but that reduces your flow rate. You can also open up your flow and get more flow, and that reduces your temperature and pressure at the inlet to the turbine. And I think what we learned is similar to what Brian just stated. You can try and optimize for your power output, and that generally means you want more flow going into your turbine, but there's other things you have to do downstream of your turbine, like cool that CO2 before it becomes a thermosiphon again. And so you kind of got to take those into consideration as well. And so you got to, like he said, kind of put the cost on each individual component and kind of design for LCOE more so than you are for direct power output. But one other thing I will definitely say that we like to brag about with CO2 and with our experiences, our first turbine that we developed was a 10 megawatt turbine to show for the Department of Energy, and it can fit on a desk at your office. Because of the density of CO2, even on the hot expanded side, it really reduces the cost and size of your turbo machines as compared to water. And it also kind of eliminates the need to do a separate cycle. You get to use the CO2 directly from your well and put it through your turbine rather than doing some type of heat transfer with another fluid. So I think those are two thoughts we have from our perspective on that.
Great. Brian, Martin, Neil, any other comments to add on this one?
Yeah, I'd like to underline the compactness of the dense phase CO2 turbine. I have exactly the same observation. I was involved in a group looking to use them for heat recovery in ships' engines. And they were so appealing because they come up really quick. You don't need to wait for steam to generate, and they're really compact.
Yeah, and I want to also, I mean, I agree with what Brian and what Jordan were saying about the thermosiphon. I just want to add to that that in CPG, in the CO2 plume geothermal version, also just like in the closed loop version that Brian was talking about, indeed you have basically liquid CO2 on the injection side, and you basically have a column of self-injecting liquid CO2 that turns supercritical on the way down. And then, and so the density is typically on average, of course, it changes as a function of depth. In the injection well, around 800 kilograms per cubic meter of that CO2. And then on the production side, once it's geothermally heated, we get in our base case where it's 2.5 kilometers down and 100 degrees Celsius for CPG, we have half the densities. We have about 400 kilograms per cubic meter CO2, and that drives the thermosiphon. We have a paper on that, on the thermosiphon effect in CPG in the journal Energy. And you can see there very well how this thermosiphon contributes. So everything I've said earlier about the mobility of supercritical CO2 being 4 times and so on, that's one aspect, and in my opinion, that's the bigger one, although the thermosiphon is the other, and it's also quite big of an effect, because essentially you do not need to pump, although we do show in another paper in Applied Energy that for CPG, if you do a little bit of pumping on the injection side of the CO2, that you get more net power out in most cases and scenarios, depending on reservoir depth, transmissivity, and so on. So, but anyway, but and maybe one other point that Brian and Jordan mentioned that is really important here, I want to emphasize this too, is that it's the enthalpy drop across the turbine that matters. It doesn't matter if it's heat or pressure energy, it's the enthalpy drop, right? And so one thing about CO2-based geothermal energy extraction is that basically you have a supercritical fluid with CO2 here that's being produced. And on the way up, it's, however, somewhat gas-like. And so it expands due to the pressure reduction. And so it actually reduces its temperature about 15 degrees Celsius per kilometer in production well. But that temperature is actually turned into pressure. And so that's why it's so important to put the turbine directly at the production well site and not to convert it over in a heat exchanger to a secondary loop and try and do something like an organic rankine cycle or a CO2 secondary loop, because you can only transfer the heat across a heat exchanger and not the pressure. So that's all very important to keep in mind when you try and want to use CO2 as the working fluid in the subsurface and in the power plant itself, in the turbine. And you basically have a transcritical cycle. So after the turbine, you cool it, you make it liquid again, and then you want to have the same injection condition as the CO2 that comes from the capture facility.
Great. Let's take a moment to come back to, sorry, go ahead, Brian.
Yeah, let me just add, if you don't mind, let me just add one thing. I agree with all of that, and these are all the design considerations. One other part about the CO2 turbine is it has an inlet and an outlet. And the outlet side tends to be one of the big challenges, because you need to return the CO2 to the high density in order for it to work in both of these open and closed loop scenarios. And as a supercritical fluid, the critical temperature is around 31 degrees C, and you just must get it down to that temperature. So the cooling requirement is significant. If you can't get down to that temperature, you need to redesign your cooling system. It's really a big part of the overall design and the location. You know, a hot location is going to be a challenge for that.
Yes, slightly unusual challenge in geothermal, having to redesign the cooling system.
If I may say
let's
something about that, also because it relates back to Jordan, and that about the cooling. And that is exactly what we see as well, that you need significant cooling in any of the CO2 usage. And it's actually so significant that this can be the highest cost of the entire CO2 geothermal power plant. And that's how we get back to LCOE. So we also do LCOE calculation and optimization and so on. And actually early on, maybe 10 years ago, when I first thought about CPG, we optimized for power output, and of course then we realized at some point that our cooling tower would be like 4 times the cost of a normal, not what you normally could afford. And just by increasing the approach temperature by a few degrees Celsius, so above ambient atmospheric temperatures, we go down by a factor of 4 in cooling tower costs. So just to say, yes, cooling is really the big key there, and the costs are substantial, and you have to be really optimized for LCOE and not for power output.
Got it. Appreciate this. I appreciate we're drawing such nuanced conclusions here. It's a bit of a different calculation from, I think, the conventional wisdom in geothermal. So I want to transition back to Neil and thermoelectrics. Could you help us draw a box around what innovations should look like or need to look like in order to be a big deal? Could you restate this is integrating an audience question. Could you restate the basic operating principle and what are the key properties you need to know?
Yeah. So what we're going to do is we're going to exchange surface equipment, generation, heat exchange, and turbines. All that disappears, and instead we have a passive semiconductor device that is placed inside the well, and we simply pick up the electrical power directly at the wellhead, and we are going to enjoy the benefit of very long life and nothing to wear out, and no surface kit. We enjoy all of that benefit. I mean, in theory, these things could last for more than 1,000 years. But on the negative side, it's not going to be extracting so much power. So the Carnot efficiency is in the order of 25 or 30% for a geothermal well, and this thing using today's materials would only recover 5%. So not 25%, but 5%. So you would be giving up a significant portion of the available power in return for the simplicity. The way, like I say, the way that they work is you've got an N-type semiconductor attached to a P-type semiconductor as cables running down inside the well and joined as a junction at the bottom. The heat is exciting the N-type semiconductor, which you may remember from school, has got an extra electron, and it's creating a bit of a distribution, and it's wanting to sort of push up towards the cold, and then the P-type, the holes on the P-type semiconductor, they fall around to make it into a circuit, but they're typically not very high power. So I'm not quite sure what the peak power would be from a thermoelectric device inside a geothermal well. It could be as low as a few kilowatts. What we would want it to be, I guess, is in the order of a megawatt. And for that to happen, needs a breakthrough in materials. One of the promising kinds would be available in bulk. It would have a high Seebeck coefficient, very high conductivity, and very low thermal conductivity. And one of the candidate materials is graphene. Graphene with some sort of doping. And of course, that is a potentially abundant and low-cost material. The reason I'm choosing to draw attention to it today is not because it's ready to go or because I work for a company that's promoting this thing, but because I believe that it's something that's worth focusing research resources onto, especially at the national labs, especially at the universities. This wouldn't be an easy subject, but it would be a big deal if we pulled it off, a really big deal. You could have these geothermal wells producing electricity for hundreds of years without the requirement for regular workovers and interventions, which might typically be required in the aggressive environment of a flowing geothermal well.
This
and I
naturally
also have a little bit of experience.
Sorry, this naturally transitions into the next point that I wanted to ask you about, Neil. So we'll start with you and then broaden it to the rest of the panel. What do you think the right source of funding is to move these ideas forward? We have the benefit of having 4 panelists from very different types of institutions, very different geographies. Are we talking about routine government research grants, venture capital, financing off an oil and gas balance sheet? We have an audience question about could we operate these in thermoelectrics on an offshore or at the seafloor in an offshore oil extraction environment? Would the proper finance be something completely different? Neil, I know this is a wide open question. I'd be curious to get your thoughts, and then let's transition that same question to the CO2 folks.
I think that the kind of funding for this one would be perhaps government funding and the work of the national labs. The kind of people that would be working on this topic are the same kind of people that would be working on superconductors for long distance, high voltage DC interconnectors. Those really amazing novel materials. I think we read recently about some people that were effectively trying to create hydrogen metal at room temperature that would be suitable for long distance electrical transmission. It's those sorts of people that would be suitable to work on this topic. And I think it wouldn't be a quick win. It would be a multi-year government-funded program.
Brian, go ahead.
Yeah, so certainly funding is a big part of getting new technologies where they need to be. And I'll cast this the way Greenfire looks at it. We've looked at large purpose-drilled well installations, say 800 megawatt power producing facility. And this would take hundreds and hundreds of wells to do. And we can scale it out to 2 to 3 cents per kilowatt hour. So it's extremely attractive, right? But the first couple wells, maybe even the first 10 wells, aren't anywhere close to that, right? So you have to get down this cost curve, and you're not going to get private investment to do the first couple of wells that way. You really need some sort of government investment, or which is out there. I mean, we're definitely pursuing and working on these sorts of projects. We've got one that's active in the geysers right now, but getting beating that cost curve down is really the secret to making these new technologies competitive with other renewable sources, right?
Brian, could we double click on that funding that you've gotten in the geysers or the project, insofar as you're comfortable? I know our audience is very curious about any field demonstrations so far.
Yeah, sorry, I didn't mean to imply that the funding is already there, right? But we had our original work at the COSO geothermal area to do a demonstration was funded by the CEC, and we have gone back to them with a really good project that we're hopeful will get funded to go the next step in the geysers and then evolve it from there.
Great. Jordan, Martin, anything else to add on this topic?
So maybe not so much on the funding, but I think you brought up an interesting question about offshore. One thing we've looked at a little bit is that we talked a lot about cooling for a second there. Offshore, you kind of have this giant reservoir called the ocean to cool your fluid back down. And so there are other challenges with offshore bringing that power onshore, but there's also some challenges that are overcome on the cooling side from a closed loop geothermal perspective.
Yeah, I have something about the funding, and that is, so for CO2 plume geothermal, the last 10 years since I had this idea when I was in the US, in Minnesota, professor there, I've been doing more or less fundamental research on CPG, numerical modeling, and so on. And for the last 5 years, I've been trying to get a pilot test off the ground. And funding for a pilot test is extremely difficult to come by, particularly in the geosciences where you deal with the subsurface and with the uncertainties there. And one particular problem I run into right now is I'm dealing with a bunch of countries all over the world with interested entities who want to maybe, and companies, or big oil and gas companies and other entities. And they're all who are interested in CPG in a pilot project, ideally where there's already CO2 sequestered to some degree in the subsurface. And the big problem I'm having right now is that you have to do this together with funding. So some money, maybe half or so, comes from the companies, and the other half comes from some government agency. And the big problem now is that, for example, here in Switzerland, it's quite hard, and for many countries, to fund a pilot project outside their own country, to take taxpayer money and to basically say, we will put a few million together with some other countries and companies to go wherever it's most conducive to do a pilot test, because we're dealing with geology. It's not like we can do it anywhere in the world, like with standard equipment development and pilot tests. We have to go, in this case, where CO2 is already sequestered for this kind of a test. And so it's really hard to put together all this funding from government agencies and companies to say, okay, we go at this location in the world, and that's where we build a pilot test. That's a huge challenge right now.
Great. I want to stitch together a couple of questions that I have and our audience has about CO2 in subsurface. So one, is CO2 expensive? Does this totally wreck the economics of a project? Two, how might we ensure that CO2 is not leaking to the surface in a reservoir or in an EGS sort of setup? And then is there a scenario, at least here in the US, where you can imagine CO2 leak off into a formation becomes a source of revenue via 45Q tax credits rather than an expense? So a lot of different topics under this umbrella. And I think, Martin, you're probably the one to start with this, and then we'll open it up after.
Yeah, so those are really great questions, and I've been working on those for the last 5, 6, 7 years, actually. And so I can take them one by one, essentially. So when it comes to so CO2 sequestration, I mean, or CPG, we're thinking about going where CO2 sequestration is already done or will be done. So all questions, issues, concerns and advantages and potential of CO2 sequestration apply to CPG as well. So it's not any different. I mean, CPG maybe helps extracting the heat energy. It helps a little bit with pressure reductions and injection of more CO2 and so on. But it can also be a bit more difficult because of potentially reactions and so on. But anyway, so all advantages and disadvantages of doing CO2 sequestration apply. And so then we answer the questions about, on top of it, what happens when you add CPG to that, when you circulate the CO2, re-inject it, take the energy out, what are additional advantages or disadvantages? And so those are, there's like you have, as an advantage power generation at twice the efficiency, but as a disadvantage, potentially that you induce some additional reactions that you wouldn't have otherwise if you change the temperature in the subsurface. So that's that. And then in terms of cost, I would say, so we've been asked this question a lot, and for our techno-economics modeling and LCOE calculation, of course, we have to consider, do we have to pay for CO2? Like maybe like some in the oil and gas industry, I don't know, $80 or something per ton. Or do we get money from 45Q in the US or something? And then and it completely changes the entire economics, if you do that. And so what we've been doing for our techno-economics modeling of CPG has been that we assume that zero. So neither do we have to pay for it, nor do we get any money for taking the CO2. And we're basically saying all of those questions are the CCS questions. And we're focusing on what happens when you add CPG to CCS. And also the leakage question, of CO2 and so on, that's also a CCS question. So those are all valid and important questions to answer, and they apply to CCS. But we focus in our research. I also do CCS research, but in the CPG research, we just say, what's the difference from by adding CPG to a CCS site in the future?
Yeah, it's a really fascinating set of questions. I see a scenario in which you could imagine a geothermal plant with a very small revenue line of CO2 storage credits, but I can see the exact opposite, where it's primarily a CO2 storage facility that also happens to do a little geothermal with a lot of uncertainty in the middle. So
depends, I just want to say to that, it depends very much on the geology. So our goal is to make CPG possible with a standard geothermal gradient of say 30 degrees Celsius per kilometer and going 2.5 kilometers down. But if you happen to be in a lucky situation that you're in one of those geothermal hotspots in the world, then CPG will crank out a lot of power, right? And then and in that case, you can maybe offset your CCS costs completely. But in other situations, maybe you can just sort of subsidize your CCS costs by providing heat, electricity, and or revenue to the CCS costs. So it really depends on the geology.
Yeah. Brian, did you have anything else to add on this topic?
You know, for closed loop, the amount of CO2 is just too small to worry about. You could use a, CCS type CO2, but it's just a really small amount. We do look at other fluids like refrigerants for power production. And in those cases, the costs of the fluids can be quite substantial, but CO2 is cheap.
Got it. So let's transition to, I think my final question before we'll turn it completely to audience questions. One thing that I've noticed over a couple of years is that relatively few people in geothermal started in geothermal. What types of people are not working on the problems that we've talked about that you think should be? What would a dream collaboration look like? Maybe let's start with Jordan and then Neil.
So fortunately for us, we've got to work quite a bit with people who are post downhole oil and gas people. And I think that trend needs to continue. I think there's lots of people that are in oil and gas or previous oil and gas that can help quite a bit in the future and have quite a bit of technology and know-how for the types of things that are needed, especially for closed loop geothermal. So I hope that continues.
Yeah, Michael, for me, what's needed is to get the cost of the wells down. And what I would like to see is a robotics team having a go at well construction so that the wells are drilled with robotic systems and looking for a 10x reduction in cost. And then in addition, I would want a team who's expert in power semiconductors, the kind of people that make those big integrated gate bipolar transistors that do the frequency modulation, those great big blocks of silicon, and get them working on a solid state device, because I don't think there's enough money in geothermal wells to pay for a lot of kit. And it's a bit like solar panels, which was where my thinking began. There's nothing very interesting about solar panels. Yeah, but that's right. That's the whole beauty of them. There's nothing very interesting. They're kind of boring. They just sit there and they make electricity and there's nobody involved. And I think it'd be great to do the same thing with geothermal wells, or at least have one version of geothermal wells that was like that. Yeah.
Great. Let's turn it over to audience questions. The first one I'll start with is, across all of these concepts, are there any oil and gas partners working on these, either with geothermal companies, with research institutes? Obviously, our audience here is heavy in oil and gas, this being a Texas-based organization. And so I'd be very curious to learn more about this.
Maybe I can take that one. So actually I was saying earlier, wanted to say that we work already with multiple oil and gas companies. I'm not sure if I'm allowed to name names here of these companies, but they're big. Some are small, some are really big companies that you all know and have heard of. And so to the audience who's having the oil and gas company, I can only say, yeah, absolutely, we do work on that. I'm a geophysicist myself, and in my research group, there are geoscientists and engineers and mathematicians and mechanical engineers and computer scientists, and we all work on this in an interdisciplinary way. But we absolutely need this connection to the oil and gas industry and to other mechanical engineers. So that's absolutely key and important. And I'm really happy to see that the oil and gas industry is more and more interested in geothermal. And about the, I want to say to Neil, so we actually work also in my research group with colleagues from mechanical engineering and so on contactless drilling methods. Actually, two of them. One is a plasma pulse geodrilling, where we generate a plasma in the rock, and then the other one is flame jet drilling, which we also combined with rotary. Then it's not contactless anymore. But that's exactly because in geothermal, the cost of drilling wells is really the highest cost in the subsurface for sure. And we need to get these costs down for any of these technologies for geothermal to make a big difference. Yeah.
Absolutely, agree with all of that. We work very closely with a number of different big companies in that area. I'd like to tie that into the last question as well. I think that the projects that we're considering are big. They're very big, and there's a lot of moving parts. And bringing all that together, the drilling, the surface part of it, every conversation includes energy storage at the same time. You've got solar fields that are installing energy storage so they can provide power at night, and you've got geothermal fields installing energy storage so they can dispatch power. And all of these things all come together, and bringing the different renewable type companies, storage, drilling, all of that into a project is essential.
Yeah, Michael, can I just also mention the Society of Petroleum Engineers? It's got 170,000 members around the world, all professional oil and gas people, many young people, and there's tremendous interest in that community in geothermal. People want to step forward into the energy transition. They also want to take forward their skills in geophysics, in well logging, in well construction, and project management, and all those other things. So there's a lot of talent there that's ready to put its hand up and sort of lean into this new industry. We just need to get it to be economic. And there's lots of people are ready to go.
Great. Turning to our next question. So everybody seems focused on going deeper and hotter in geothermal. Is the same true for CO2 and for thermoelectrics? Or do things like corrosion start to become issues at really high temperatures?
So maybe I can say something about that. So for CPG, the whole idea is not to have to go so deep and so hot. So essentially, the way of thinking for CPG, for CO2 plume geothermal, where you release the CO2 as opposed to the closed loop CO2 EGS system. But for the CPG system, the idea is let's use CO2 that doubles roughly, as we talked about earlier, the electricity generation efficiency. That way we get away, let's say, with only 100 degrees Celsius in 2.5 kilometers depth with a regular geothermal gradient to economically, with levelized costs of electricity that are competitive, generate electricity. So the whole idea is by using CO2 in this way, we don't need such high temperatures. Of course, we take it. If we are one of the hotspots in the world and it's hotter, wonderful, but we don't need to. And so with 2.5 kilometers, we can already at economic cost generate electricity, we think, in the future, if but so this is exactly the opposite of going as deep and as hot as possible, but rather exchanging the working fluid in the subsurface to get away with lower temperatures than normal.
So we do a lot of downhole work, and I would put this in two categories. One is We have a technology where we circulate CO2 in a closed loop heat exchanger that creates a fluid flow in the reservoir. And that doesn't require hotter or deeper, it just requires a large amount of steam in the reservoir. But we also design for hot, dry rock. And hot, dry rock is really, you know, just there's so much opportunity in hot, dry rock as long as you can make it economical. And in every case, hotter and deeper. It doesn't matter. It doesn't matter what you're spending money on. If you can find something that's hotter or deeper with CO2, the power just it goes up exponentially faster than the cost.
I will say, in addition to that, although I agree, and Brian's mostly correct, one of the nice things about CO2 is that it can work at lower temperatures. So although hotter and deeper is generally better from a power perspective and from a cooling perspective, it doesn't have to be. So if the LCOE, if digging too deep really hurts your upfront costs, CO2 can still work at these lower temperatures, 80 to 100 C, coming out into the turbine and still generate pretty significant amount of energies.
I will say though, we've done simulations on CO2 in both EGS systems, so the CO2 EGS systems, and in CPG. And it turns out that if you're below 5 kilometers, actually water is better than CO2 from an energy extraction perspective. So it does not get better with greater depths than say 5 kilometers. The power generation output is pretty much crossing over, and it's the same. And at some point water is better. And that several publications, including ours, have shown that. So I would say that, however, just because the power is slightly less by using CO2, maybe at really great depths or deeper than 5 kilometers, can still mean that CO2 is a desirable working fluid, because maybe if it's CPG, you want to do CO2 sequestration, although at that depth you probably don't do that. But the other reason is that you can use about an order and a half lower permeability, so let's say transmissivity, so permeability times the reservoir thickness, than with water. And so that's a big difference, right? So there's multiple reasons, and you have to weigh them against each other. But it is not true that just the deeper you go with CO2, it just gets better and better and better. At about 5 kilometers depth, it crosses over in water. From a power perspective, actually the better working fluid.
Got it. Going back to the corrosion question, Jordan, I think this might be for you as the power cycles person. From my vantage point, I know there are trade-offs, at least in the subsurface, between water and CO2, and I think CO2 is generally thought to be a little bit more benign. But within the power cycle, Jordan, do you anticipate significant corrosion issues as a function of temperature and switching to CO2?
So, not to the extent of some of the oxy-combustion we look at for different power cycles. So CO2 and water does become acidic, and so there is definitely things you have to take into consideration, but it's quite a bit lower because of the low temperatures. And so although that does mean that you probably are looking at some type of stainless steel, it doesn't mean that you're looking at super alloys or other ways to reduce that from what we've seen. And it's even better if you're assuming closed loop, because you have a little bit more control. If CO2 is pure CO2, then there's really no consideration from a corrosion perspective. But it's just when it starts mixing with water that it becomes slightly acidic.
Mm-hmm.
If I can just say about that too, I fully agree with that. And you get carbonic acid essentially, but it's a weak acid, and there are solutions for it. It's a bit more expensive, but yeah, there are solutions for it. And maybe one quick thing I want to say, about what I said earlier. Just to clarify, and so there's no mix-up. So for closed loop systems that Brian is looking at with CO2, of course, the deeper you go, the better. Just to just to be clear that I was talking about open loop systems earlier when I made the statement.
Yeah. For hot dry rock, no matter the fluid, hotter and deeper is makes it.
No. I was saying that for hot dry rock, for anything with open loop, it's at 5 kilometers. It's water is actually better, but there may be other reasons why you use CO2. But for your closed loop system, there the deeper and the hotter, the more power you get out. Indeed.
Yeah, and to combine that with what Jordan said, hotter makes more power, but with CO2, it doesn't need to be hot at the surface, like Jordan had mentioned. And I think Martin said that too. It cools itself on the way to the surface by producing pressure.
Got it. And then Brian, I think this question is probably best started with you, given that Greenfire views CO2 as more of a drop-in for water than maybe other approaches might. How would you compare CO2 against other working fluids such as ammonia, ethane, propane, isobutane, and the like?
Yeah, so there's two interesting parts here. So we do consider all fluids because we can. It's easy, right? And some refrigerants do have some interesting characteristics. It's usually resource dependent. What the temperature and depth is and what the practicality of the diameter that you have access to. If it's a retrofit, you're usually limited on the diameter. And CO2 is a lot cheaper, and some refrigerants, maybe the owner doesn't want to put those in the well, right? So there's some limits there. For opportunity, modeling, we do lots of process modeling. Modeling a pure fluid is fairly easy. I think there's a lot of opportunity at looking at mixtures of fluids for closed loop. So can you put in 5% of a refrigerant with CO2 and change that heat rejection part of the equation, or change the density or the heat extraction? There's really a lot of opportunity in developing that. So we see this as phases. Water, there's no real challenge there, right? CO2 adds a little bit more challenge, but some opportunity, and then you can keep going.
Anyone else have comments to add on that question? If not, we can move on. All right. Do these technologies we're talking about, the thermoelectrics and CO2 as the working fluid, do they work equally well everywhere? One audience member asked, do the economics of CO2 go out the window if you're not near a large body of water for cooling, for example? Are these technologies more amenable to certain resource temperatures, subsurface characteristics, or certain surface environments? Maybe let's start with Neil.
Yeah, well, I think the interesting thing about something that's passive, like the semiconductor thermoelectric generator, is it can pretty much go anywhere. It could even go in some old oil wells, frankly, because all it's needing is for the bottom to be in the hot and the top to be in the cold. It doesn't need an advanced completion. Secondly, it's a pretty tough material. And the existing thermoelectric generators that we have in use today, which are made of semiconductor, are sitting on gas turbine exhausts. They're operating at 600-700 degrees centigrade. So they could certainly also go in very deep wells. And the main drawback is that they're not recovering so much power. So they would have to go in a well that was cheap. Because it wouldn't be generating enough electricity to pay for one which was very expensive.
Go
ahead, Brian. Go ahead.
Just quickly, I think the project details are so essential, but probably one of the biggest factors is what's the cost of electricity? What's the growth in electricity? And we do a lot of work in the Pacific Rim. And some places are just a lot more attractive to develop than others, not on the geology as much as the cost of power. Go ahead, Martin.
I would say that you know, in geothermal we generally have the problem that we don't have a big temperature difference between the subsurface and the air, right? That we reject the heat to. It's not like in nuclear power or fossil fuel power. And so this is a bit, and it's even worse. The person who asked the question is absolutely right. I mean, with CO2 we have this even larger cooling need, and so if we are in a region where we don't have a lot of cooling water, it can be really a problem. And so we looked in the Middle East at some, and also in Texas actually, calculating the LCOE and how, you know, with the cooling and everything. And so it really is a concern. But then also there are other regions. We looked at, you know, for example, North Dakota and many other regions where you have, and here in Switzerland in the winter at least, you have really cold temperatures. And there are, this may be a bit strange for the US perspective, but for where electricity is mainly needed or a lot needed in the summer and during noontime for air conditioning, electric air conditioning, here it's exactly in the winter time for ground source heat pumps for heating, actually, to provide the electricity. And there's more countries where this will happen. And so I think geothermal has, for electricity generation in particular, has quite a bit of potential for that purpose, providing electricity, particularly in the winter, where the efficiency of geothermal for electricity generation is quite high. And you do need a lot of electricity, particularly in the winter. Yeah.
Okay, we'll do two more quick audience questions. One, so given issues around things like water scarcity, wastewater disposal, and I'm thinking about the American West, you know, where most of the geothermal resource is here, but it could apply to a lot of areas. So given these issues around water, if CO2 becomes a reality, why would we ever bother using water, or would we?
That's a that's a convoluted question that's hard to answer. But cooling, you know, in the West, it's just so much more efficient, and you make more power if you cool with water, right? And but if you don't extract water from the resource, then the resource will last a lot longer. And so there's been a lot of decline in the geysers, like really in the amount of megawatts that can be produced, and there's really as much water as can be put back into the resource as possible. But yeah, why not leave the water there from the beginning and use something else to cool and have a lot longer resource? We support that.
I'd like to add as well, we've talked a little bit about cooling. And although I think that is one of the bigger challenges that needs to be figured out with CO2, one of the nice things at least is that, as Brian pointed out, the critical point of CO2 where you're kind of trying to get your cooling to is at about 30, 31 degrees C. And although the summer in Texas, that's right around where you are, most of the US average temperatures are in the 21, 22 degrees. And so dry cooling is an option for a large portion of these types of CO2 wells. And I'm not saying that that is the answer, because there's still some footprint and economics things that you have to deal with, but you don't have to use water at that point. You can run CO2 directly through your dry coolers. So there's no heat exchangers or that type of thing. And so, and you can reject right to ambient temperatures for a large portion of the United States and Europe as well.
Okay, well, we'll have to pause there because we've got 5 minutes left. We hope you've enjoyed the discussion so far. I want to wrap up by giving each of our panelists a chance to leave us with a closing thought. Let's go in reverse order this time. So we'll start with Neil, then Martin, then Jordan, and then Brian.
Yeah, my closing thought, Michael, is that 40 years ago, you know, silicon solar panels were a novelty, and they didn't look like they were going to be any good. And here we are 40 years later, and you know what? They look pretty good. They're pretty much the lowest form cost of renewable power. And I think if we put the same amount of effort into solid state geothermal, we could do the same thing. We need to be patient and commit the resources.
Yeah, so my closing thoughts here are on, with respect to CPG, are that essentially you get two things for doing CO2 plume geothermal, but when you combine CCS with geothermal energy extraction with CO2, on the one hand, you increase the geothermal resource base because you can use many more regions worldwide wherever you can sequester CO2 at 2.5 or so kilometers depth for geothermal energy, electricity generation at competitive prices. So it's basically an increase of the geothermal resource base. And so that helps spread geothermal. And the other advantage is that you subsidize CCS. So you basically decrease the costs of adding carbon capture and storage, not just to power generation, fossil fuel power generation, but to cement manufacturers, so anyone who has a point source CO2 source. And so you basically can use the technology to offset some of those costs. And if you're lucky and you're in a geothermally very hot or exceptionally hot region, you can even potentially completely offset the CCS costs by revenue and electricity and heat. And maybe even go beyond that, but that's for special regions. So that's sort of the double thing: expanding the geothermal resource base plus helping CCS be more economical of CO2 plume geothermal. Thank you.
I guess for me, being on the turbo machinery side, more so than the physics side, I think my closing thought is we've done a lot of research over the past couple of years, making up lots of technology gaps for CO2 turbines, especially at hotter temperatures. So I think the technology is in a great place to be applied from a turbine perspective to this application. Not that there's no challenges, but I think lots of those technology gaps have been made up recently over the past few years.
So first of all, thank you for this discussion. It's been great. It's been wonderful talking to all of you. My closing thought on this is that there's really a lot of new technology opportunity. Certainly with CO2, possibly with other fluids, it really takes combining a lot of things together. And that takes investment. I think that's really the top level vision of all of this, is that we need to do these sorts of renewable power projects. We need to do it at a large scale, and the investment to do that needs to be there. Thanks.
Great. Thank you very much, everybody. This wraps up our discussion. We hope you've enjoyed the panel, and we hope you enjoy the rest of the conference. Thank you.